Good morning, everyone. I hope your Monday morning post Super Bowl is going well. We're gonna get back into maybe some warmer weather for a while, but it's not raining, so it's very pleasant. So please enjoy the nice weather. Today, what we're going to do is discuss the concept of work and how we can use the definite integral to compute work. Now, all of this material that we do today, of course, will not be on the test that you have upcoming. So this will be second test material, but we have to move on, unfortunately. Now on Wednesday, what I've decided to do is we won't have any formal lecture, but I'll just do some review. Probably just get an old Calculus 2 test and work through some examples just to kind of give you an overview. I know a lot of you probably study on your own and you like to have that personal time, but this way I can do examples. Like I say, the format of the first test will be a multiple choice. And so when you look at the practice test, you'll see that there's multiple choice and free response. But basically, you'll work the problems just like you do in WebAssign. And as I said before with the announcement, you will write out your work, in numeric order. Problem one, do the work. And this way I have evidence of your understanding. The main thing is just to look at this like a face-to-face class where you show your work. And that means that for instance, if you select a right answer but you don't show any work, then you can't get full credit. But if you select a wrong answer and you do really nice work and you've got some careless errors or you just have some minor issues, then I can award partial credit. It's with an online class, I want to make it fair, and I want to be sure that you are credited on the major test for your work. The quizzes and the homework, unfortunately, you have to do correctly. You have plenty of leisure time to get ready for that, and it's a much more relaxed setting. But for the test, I do need to see your work, and I'll say more about that. I'll have the Turnitin app. I'll just make a little block on Blackboard for test one work, and it'll use the Turnitin app, and you'll just upload your one file of your work. And again, you probably done this for other classes, but all of your work needs to be scanned and put into one file. And that one file, when I grade your test, I will have right in front of me. So it'll be like having your paper, but in the virtual setting. So again, remember on Wednesday, we'll do some review. Like I say, everybody's different about review, and it may be something you like or don't like, but I'll give you that option to take advantage of that. Now let's go ahead and look at the topic for today, which will be work. I think I think maybe some of you are in if you're in Calculus 2, you're probably taking a university physics now because I think the Calculus 2 is like a co-requisite. And so you talk about a lot of things that utilize the integral. And so work will be one of those. Now, the first thing we want to do is, for instance, discuss work as it relates to springs. And then the second thing I want to do, excuse me, is to discuss work when it comes to moving liquids around. That's probably the most complicated aspect of work, and again, a very useful one. Your future engineers will certainly need to know how to move liquids around, especially if you work in the chemical engineering industry or mechanical or civil. So first, what we want to do is look at Hooke's law. Hooke's law. So when we think about work, and this has to do, ladies and gentlemen, with springs. So when we think about work, we think of informally force over a distance. Force over a distance. So the idea is that when the force is constant, you have much less work to do because it does not vary as the horizontal component, whichever direction you're moving varies. But in most cases where the calculus is required, you have a variable force. So for variable forces, we must use calculus to compute work. And again, just like in all the problems we've done before, arc length, volume of a solid of revolution, areas, this is a summative process. We use the partition to chop up the interval and to sum, and then in the limit produces the Riemann integral. So like I say, we're stuck with calculus because it describes how we interact with our environment. Now, with the Hooke's law, we have the following. So this will be for stretching and compressing a spring. And the law is very simple. In this case, we have force, and we're thinking magnitude, not a vector quantity. So I'm not going to have any direction associated with this. So force will be F of X will be Kx, where K is a constant which depends on the spring. And X is the amount, and I'll just say in length units, that measures compression or stretching. So again, a very simple law with the magnitude of the variable force. And so, for instance, you might be given a problem where you have to determine K because they gave you a particular force that was responsible for a certain distance X, be it compression or stretching. So let's do a very simple example of this. This is a good way to get started with work, and it kind of guides you into the moving of the liquids, make it a little bit easier. So here's an example. A force of 20 pounds stretches a spring 9 inches, and I'll go ahead and write this out, 9 inches in an exercise machine. Find the work done stretching the spring 1 foot from its natural position. So again, this is a very simple and straightforward problem. Not every problem has to be difficult, but it's a good way to get started with these ideas. So notice we don't have a K for this particular spring and we can solve for it. So first, solve for K. Don't worry so much about units until we state the final answer. I know in physics, you're a lot more worried about that, but the work in this case will be in foot-pounds. Or for instance, if we're using MKS units, it will be Newton meters. So solve for K. So we have force equals Kx from Hooke's law here. And so we have a force of 20 pounds. And now, of course, we've got feet here and inches here. So we'll have 9 inches, 12 inches, like we're in pre-cal, 1 foot. So this is 9 over 12, or 3/4 foot. So now we can substitute. So we have K times 3/4. And now we can just cross multiply. So K, in this case, will be 20 times 4/3, or just reciprocate. That's probably the easiest. And that's just 80 over 3. So here's our constant for Hooke's law. And so now what we want to do, again, we're stretching the spring and the force is varying. So we can say now, just to write this down, to tabulate, f of x is 80 over 3 times x. So we have a variable force. So as we stretch, we have to think of taking this interval from 0 to 1, x element of 0 to 1, and partitioning it. And for each subinterval, we are applying the force. So we have the force times the distance. Now this is very simple compared to what we've been doing a lot, well, at least for this particular problem. And so we do this for each subinterval, but in the limit, that just means we're computing the integral. So for instance, we could say in this case, the change in the work for a particular subinterval will be 80 over 3 x times delta x. So the idea here is that we're not being as formal as we were before, like with the subscripts and things like this. So this would be per interval, and now we can sum over the entire interval with the integral. So this implies work equals the integral from 0 to 1, 80/3 x dx. So our game plan has not changed at all. We really do keep doing the same thing over and over, but some of the problems get very tedious. As you've seen, lots of algebra, lots of analytic geometry, and then just barrels of arithmetic, fractions, radicals. I mean, you just kind of stuck with it. The calculus gives you that, but here it's not so bad. So now we have 80 over 3, and then we can add 1 divided by the new power, x squared over 2, integrate our limit 0 to 1. So now we have, if you like, we have 80, and we have 2 times 3. We'll just go ahead and bring the 2 and the 3 out. And of course, we'll have 1 squared minus 0 squared. Now, of course, the 2 will divide into the 80 to give us 40. So we have 40 over 3 times 1 minus 0, which gives us 40 over 3 foot-pounds. And I'll just use the LB abbreviation for pound with the English units. Now, of course, what's important here is that when you do a work problem, like if you're maybe lifting a chain or something, you think about the chain having a linear density, like a certain force per foot or inch The idea is we have to think dimensionally depending on the particular scenario that we're dealing with. And so it's usually not very difficult to figure that out. But here's one other example that working with the spring that I thought was interesting that turns things around a little bit. It gives you the information in a backwards format, which I think is interesting to see. So let's go ahead and look at this. And in this particular case, we have 6 joules. So this will be in the MKS, 6 joules of work, that would be a Newton meter, is required to stretch a spring 1/2 meter from its natural length. And then it says, find the work to stretch the spring an additional 1/4 meter. So in this case, we're actually given the work. Where in last case, we computed the work, and then we're going to have to compute some more work. So when we look at this particular example, we can still solve for K, but in a different way from the last problem. So in this case, when we starting, we have X living between 0 and 1/2 from here, required to stretch a spring 1/2 meter from its natural length to give us the interval of integration. It's always important to make sure you get that interval of integration. It's easy to be pushed in one direction by the problem, thinking that the problem is going to, okay, this is what you're given, that's what it should be. But everything has to work together. So be careful when you're choosing your interval of integration. I mean, that's probably one of the more difficult parts of the problem. And so now we're thinking, okay, so this implies we have 6 joules of work. So the work is 6. And we have the integral 0 to 1/2. And then we have fx, which is kx dx. So again, this is Hooke's law. So just remember that the variable force is kx, Hooke's law, the magnitude. And so here we can solve for K, but like I said before, in a different manner. So this will equal, we can go ahead and just write this as K times the integral 0 to 1/2 x dx. And we always wish all of our integrals were this simple. So we have K times x squared over 2, 0 to 1/2. So this gives us K over 2, and then we can substitute. So we have 1/2 squared minus 0 squared. So we have K over 2, and then of course this will give us a 1/4 minus 0. So we've got K over 2 times 1/4, which is K over 8. Again, very straightforward, but every instance that we work, it's important. It's an important part, right? So now we can solve easily for K by multiplication. So if and only if K is just 6 times 8 or 48. So now this implies that our force, variable force, is just 48x. Now we have stretched the spring to 1/2 meter, and it says, what is the work to stretch an additional? So if we start at 1/2 and then we go an additional 1/4 meter, what kind of problem will that require? Well, of course, we can just say, okay, what's the right end point? Well, let's just work it out. 1/2 plus 1/4, common denominator of 4, so that'll give us a 2 plus a 1. So the right-hand endpoint in this case will be 3/4. So this implies x lives, in this case, between 1/2 and 3/4. So this would be our new interval of integration. Now, again, this problem is not overly difficult, but it's a little bit busy in the components. But again, very straightforward calculations. So now, by definition, the work that we need for the additional stretching will be the integral from 1/2 to 3/4. And then we have our variable force, which is 48x dx. So we'll go ahead and factor the 48. So we have 1/2 to 3/4 x dx. And our good friend, add 1, divide by the new power. So we have 48 times x squared over 2, 1/2 to 3/4. So we can move the 2 over. So we have 48 over 2. And then we can substitute. So we'll get 3/4 squared minus 1/2 squared. And of course, here division by 2 will give us a 24. And so now, upon squaring, we have 9 over 16 minus 1/4. So we can just do a common denominator. And then, of course, these are easy numbers. So we just have a 4 here. So we have a minus 4 here. So we have 24, 4 times 4 for the 16. And of course, 9 minus 4 is 5. So this gives us 4, in this case, times 6. Oh, well, let me go ahead and break it down a little bit more. We've got another 2 in that other 4. So we have 2 times 3. And just break down the 4. In each case, the 4 and then the 4 here, 2 times 2 times 5. So of course, the 4 and the 2 all absorb, and that leaves us 3 times 5 over 2, or 15/2. And in this case, this would be joules. Yeah, that didn't turn out very well. Let me make that a little bit better. Okay, so again, not an overly difficult problem, but a nice utilization of the understanding of Hooke's law given different hypotheses. So I think as you do your problems, you understand the technique, but when you read the problem, we often bring in preconceived ideas about what the problem should be. And as a math professor, that's one reason I like certain homework systems like the WebAssign. Dr. Larson will give you ideas to think about, and we always assume certain things, which in many cases is good. but we don't want to assume things that don't apply. So we can't force a hypothesis on the problem that's not there. And a lot of times when we do that, we skew the problem and then wonder why we're not quite getting to the finish line. So again, just remember, making certain assumptions is actually quite useful, and in many times to do problems required. But make sure that the requirement uh, that you're adding supports the problem and does not change the problem. There's a big difference. We don't want to change the problem. We simply want to amplify it in a way so we can actually compute it. Now, what we want to do now, and this is a focus that I actually like teaching. It's kind of like doing arc length. There's always something fun to do. We want to move water around. So the idea of pumping water to different locations, from one location to another, is certainly something that occurs quite often in our world. And so the idea is that, kind of like doing the volumes of solids of revolution, we're always paying attention to the geometry of certain objects. And so now if we have tanks that hold water or some type of liquid, we have to pay attention to that inherent geometry to move liquids around. So let's look at that. So here, I think you'll enjoy this. So example, we have a rectangular tank. We'll start out simple. Always say that, but every problem has its difficulties. Rectangular tank with, let's see, we'll just say rectangular tank, and I'm just going to say the base is 4 feet by 5 feet. Okay, so we've got a nice rectangular tank, a box, so to speak. The base is 4 feet by 5 feet. And we're going to assume, we're going to say tank. The tank is full of water. Now, like I said before, there's a constant involved here. When we're moving liquids, I'll just use rho like we will use when we do center of mass. That's a Greek rho. It's not a P, it's a rho. So when you type a rho, especially with the center of mass, you use the little palette that has the Greek letters. So that's not a P, it's a rho. And I'll try to make the difference, that it's more smooth there. And for water in the British units, this is 62.4 pounds per cubic foot. That's the weight density of water. And then it says water is pumped over the top edge. So water is moving to the top of the tank to be removed. Now let's do two computations here. And we'll draw a nice picture. Compute work to empty half of the tank. Now, in this particular problem, we're assuming, and you have to make this assumption, that we're going to remove the top half. I mean, you're thinking if we started at the bottom and drew out the water that way, then that of course would require more work. So the problem in this case assumes we're removing the top half, and then in the second part of the problem, we remove all of the contents, where of course the hose or device that would be removing the water would be at the bottom of the tank. So that's just a small assumption, though an extremely important one. So let's just go ahead and draw a picture of what we have. again, this doesn't have to be Rembrandt, but it's nice to have just kind of a little visual of what's going on. And of course, as you set up a problem, if you're working out in the field, then you have to keep track of all of the particulars of the problem, because it does change the computation. So we'll take y and we'll take x and we'll take a 0 here. And what we'll do, we'll move out to 4 here, and then the breadth will be 5. So in this case, if you like here, I don't even have to put the 4. I'll just notate the actual distance, because we're not really going to be worried so much about the distance here. Our scale, our interval of integration will be on the y-axis. And so we'll note this as 5 feet. Tried to draw the T first. There we go. Just to kind of give you an idea of the geometry, I mean, this is where we get to draw like we're in art class. Okay, so we have this box here now, which is full of water. Now, the idea here is that we want to remove the top half of the volume. So what we're going to do is let y live between 2 and 4. And so we can mark this off here as 2, and then here 4, and we'll just take a y in that interval. And now what we can do is draw a slab of water of thickness delta y. Again, this is just giving you a visual of the geometry. And so we think of this as a slab of water. Here's our slab of water. And then, of course, it has a thickness delta y. So when we think about moving this slab of water for a particular subinterval in the partition, we've got to move it a distance. And so we can mark off the distance here, which will be d equals 4 minus y, just like we're doing the arc length problems or the shell method, where we're having to write down distances like the length of the strip or the distance to the axis of revolution. All these kinds of arguments and techniques we do here. So that should be something that you're familiar with. So now just like with the spring, we are moving over a length. Here we're taking a volume that we're moving a distance, and that's why we have the cubic units here. So basically for every cubic foot, we have this much force in terms of pounds. So what we can do is say delta V for this particular slab. What's the volume? Well, again, we have the 4 times the 5. That is the area of the slab, and then the volume we get by multiplying by delta Y. So again, this gives us 20 delta Y. And then we say, well, what's the force exerted by this particular slab of water? Well, it will just be the weight density times the volume. So we have in this case, and we'll just say rho times 20 delta Y. And then we can just write that as 20 rho delta Y. Again, when you're doing your computations, write the weight density as rho. Don't just write the number until you get to a point in the calculation where you can substitute it and then compute. That would be the easiest way to do, so you're not dragging a bunch of numbers along. And then the work for this particular slab will just be, in this case, the force over the distance. And of course, the distance in this case will be 4 minus y. So if you like, this will give us 20 rho 4 minus y delta y, just like we did for the spring. Now, the idea here, ladies and gentlemen, is that it's probably a little bit more important, kind of like we're doing the arc length and the volumes of solids of revolution and things, where we do our work, our sidebar work. This is really important. So if you try to just jump to the integral without thinking about some of this, it may pose some deficiencies when you start to do the integral. So maybe it's a good idea to work this out, and then you can go directly to the integral, having confidence that you set up. And then of course you can always go back and check your work, and that's imperative. Write enough so that you can go back and see what you've done. So now this implies if we want to empty half of the tank, and we're in this case assuming the top half, we're going to integrate from 2 to y this particular expression. So we have work, I'll write it out. Work equals the integral 2 to 4, 20 rho 4 minus y dy. And so now we can use the linearity of the integral, go ahead and factor the constants. So we get 20 rho integral 2 to 4, 4 minus y dy. Now, of course, we can just make this table ready. We have the u here, u equals 4 minus y, du is negative dy. So we kind of lament the miscellaneous substitution because that's just a complete transformation. We're happy to get basic substitution. So now we'll have a 20 rho, and then we'll pay for that -1 that we're going to put into the integrand here. So we have 2 to 4, 4 minus y, and then we'll just do a -1 dy. Or you could just write negative dy. They accomplish the same. And now, of course, this is table ready. Integrals are our friend. But you can see as we do these types of calculations that again, it's like doing the optimization problems. We have a lot of preliminary work, and then we have to compute, we have to do the calculus. And so there are many parts with these problems. So now we can go ahead and complete this. This is table ready, add 1, divide by the new power. So we get -20 rho. And so we'll do that. Remember, that's just a 1. So we get 4 minus y squared over 2. integrate 2 to 4. And now, if you will, we can go ahead and readjust the coefficients. So we have negative 20 rho over 2, and then apply the limits. So we get 4 minus 4 quantity squared minus, and now we have 4 minus 2 quantity squared. So again, the 2 absorbs into the negative 20, so that gives us a negative 20, excuse me, a negative 10 rho. And then, of course, here we get the 0 minus the 2 squared, which is a 4. So again, 0 minus 2 squared, 0 minus 4. And so now when we multiply, notice the negatives absorb and we get a 40 rho. Well, isn't that nice? I mean, that's like, you know, that's a gift. We got a coefficient of rho that has a 0 in it. So how nice. So now we can go to the rho and make a substitution for that. So this will be 40 times 62.4. And of course, the 0 will retire the decimal. So we get 4 times 624. And we can easily multiply that out. The 2 4s will give us a 16 with a 1, that'll be a 9, and then a 2 4 foot-pounds. So again, like I said before, don't run the number through the calculation. Just give it a nice symbol like we're going to use when we do center of mass. And again, remember, this is the Greek rho. The Greek rho is RHO, and it has this. It looks like a P, but it's a lot more rounded. And as you well know, the formatting is important. Think about what the computer algorithm does. It scans what you type when you do your homework or you do your quiz. And so if it is specified that a particular letter must be used and a particular font, you know, we think about this, or uppercase, lowercase, the computer algebra system code scans that. And of course, if it sees something that's foreign, then that kicks out the answer. So it is artificial intelligence as much as we can stand and afford. But remember, for the most part, WebAssign is on your side. I've had students, you know, they always test out WebAssign. They'll leave their answer exact, and they'll just type every number in and not multiply it out like we did here. And usually WebAssign will give you a thumbs up. So as you do your homework, you can always test. It's like, well, this is the same thing, it's equivalent. See what WebAssign thinks, and usually it turns out in your favor. Okay, so now let's do the entire tank. Now, we don't have to draw a brand new picture, but now we're going to think, let me just go back to our picture. We're going to think that now we're removing from the bottom all the way out. So here we're removing the top half. Now we're going to remove all contents. So that's just going to be a minor change, but it's an important change. So I want you to see it. So for B, compute work to empty the entire tank. So all the contents. So now when we actually do that, when we do that now, this implies that we're going to go to the very bottom and start to remove all of the contents. So this would, the major change is right here. Y lives between 0 and 4. And this is an important change. So when you think about this, then this implies this is the only difference. Everything else is the same. So let me go back here. and just say we have the same computation here. So just go ahead and write this down. Delta work, or delta W, will be 20 rho 4 minus y delta y. So this is the same computation. Now we're just allowing y to live in the lower part of the interval, but that does not change the computation. If y is down here, the distance is still the same. The delta v, the delta f, all the same. So that does not have to be recomputed. So now this implies that the work will be the integral, in this case, 0 to 4. 20 rho 4 minus y dy. And now, of course, we've seen this before, so we can go ahead and dress it up. So we have 20 rho negative 1, 0 to 4, 4 minus y, just put to the first power, negative 1 dy. And of course, this is table ready. And so now as we compute, we have negative 20 rho times 4 minus y, quantity squared, divided by 2, 0 to 4. Well, at least with this problem, we get a lower limit of 0, so that's nice. So now we have negative 10 rho over 2. And now as we compute here, we have 4 minus 4 squared, and then the 0 limit, 4 minus 0 squared. So just a minor change. And so now, of course, this gives us the negative 10 rho since the 2 absorbs into the 20. And then, of course, we have a 0 minus a 4 squared. So this is 0 minus 16. So now we have a negative negative. So we've got, in this case, 160 rho. Now, when you actually do this, you can break this up into 2 pieces. We can just say, in this case, 100 plus 60. Now one thing that we can actually do that would make the calculation simpler is this. Before I do this, let me just show you a little trick here. This will lessen the difficulty of the calculation. Do 160 and then substitute the 62.4. There's a reason for this. Let's go ahead and retire the decimal. So this will give us 16 times 624, which is an easier computation. And now we can just say, well, this is 10 times 624 plus 6 times 624. Of course, we don't go forwards to go backwards. This is backwards factorization. When we use algebra to compute numbers, we're usually going in the opposite direction. So you have to kind of force yourself not to go backwards once you've moved the calculation to a better level. So now, of course, here we just add a 0. So we have 6,240. And here we can easily multiply this. That gives us a 24 with a 2. So that's a 14 and a 1. So we get 37. So now, of course, these are all 4 digits. So we have a 4, and then a 4 and a 4 gives us an 8, and then a 7 and a 2, a 9, and then a 3 and a 6 give us a 9, and this will be foot-pounds. So 9984. So there is a big difference, and we expect that. But again, I will always make it clear when I give you a problem on a test as to what you're asked to do, where you don't have to make certain assumptions. When it comes to math problems, you don't want to overdo the hypothesis. You do want the student to think, but you don't want it to be unclear, okay? Because For instance, if you look at a problem a certain way, that can potentially change the answer. So I want to make sure that as you have examples on your test that it's clear what you need to do. Unfortunately, not knowing how to do it is not an issue in your favor. I find there's always a nice point where you move beyond, where you don't question everything. As you learn, your confidence level is low. But as you start to practice more, then you get beyond that and you're like, I've got confidence. I know I've set this problem up. This is what Professor Ron did in class. I know how to do this. And so you don't question as much. And that's a much better feeling. Okay, now let's continue to change the geometry. The geometry is what is the difficulty in all of these problems. And this, again, even though this is not on the test, the types of calculations we're doing will be very beneficial as you prepare for this test. So this is good. And if you have time to go ahead and work through some of these, if you're all caught up, fine, but it's still good practice. So in this case, we have a cylindrical tank. We have a cylindrical tank, and in this case, we have a height. We have a height of 4 meters, and we have a radius. So the dimensions of the cylinder, a radius of 2 meters. And the tank is buried. So I kind of think maybe what we would see, some tanks are buried. We're going to have a problem where the tank is resting horizontally, but this one will be the vertically placed. The tank is buried so that the top of the tank is 1 meter below ground level. And you can think, like I say, gas stations. And in this case, the tank is full of water. And then what we're asked to do is compute the work to pump the contents of the tank to ground level. Compute work. And let's just say here, yeah, let me just kind of underline that. It's full. Compute the work to pump the contents of the tank to ground level. Now, again, these are all standard questions that never seem to get old. I mean, it doesn't appear that the calculus will ever leave us. But when you think of this, you're thinking, okay, we've got a MKS unit. And so in this case, the rho is actually 9,800 newtons per cubic meter. So we have the rolling D and the rolling T when we pronounce English, and of course when we're trying to make an impact, we kind of focus on consonants that aren't really to be pronounced that way. I had a student say, "Well, you always make sure you get that last syllable." I said, "Well, don't tell your English professor because they'll get mad at me." But yeah, we often emphasize certain consonants just to be hopeful that everyone's listening. So now what we can do in this particular case is sketch this like we did for the rectangular tank to notice what the geometry is. And so just like in a physics class, you orient the geometry so that it's easy to assess. You know, we like to put things, orient the axes so that we simplify the algebra. So we'll think of the axis of the tank as being the so-called y-axis. So we'll have our ground level. So this will just be the ground. And let's just go ahead and mark this off. Now, we know the height of the tank is 4 meters. So we can start at 0 here, and then this will take us to 5 here. And then, of course, we can say 4 here for the top of the tank. And I'll go ahead and draw our nice little picture for our tank. Again, a little bit lopsided. So when we look at this particular picture, this is kind of like where we've got a situation where the water will move for 1 foot outside of the tank. And so our interval of integration will change due to that. And that's what makes these problems a little bit more complicated. So now when you look at this example, once we get out of the tank, we have an additional meter to move the water, but outside of the tank. So this implies that our interval of integration will start at 0 and end at 4 with the tank. So now if you like, we can mark off a Y and mark off a disk of water. And so now we can see that the distance, this is where the 5 comes into play. The distance that the water moves is 5 minus y, where the actual interval of integration runs from 0 to 4. And so we get a slab of water in the shape of a disk. So now we have a delta y. And then if you like, we can go ahead and mark in the radius. The radius here is 2. And so you're thinking this reminds us of the disk method. So again, we've got a fairly straightforward volume setup, just like with the rectangular tank. So what does this give us? So, and I'll go ahead and mark off the X here. The volume will just be the area of the circle of the disk times the actual thickness. So we get pi r squared. Of course, the radius of the disk is 2 r squared, pi r squared times delta y. So 2 squared is 4. So this gives us 4 pi delta y. And now the force exerted, and we'll just use rho, will be rho times 4 pi delta y. And we can just rearrange this, if you like, to 4 pi rho delta y. And now, of course, the force will be exerted over this distance here. So the work for this particular slab will be 4 pi rho delta y times the distance 5 minus y. So this is where you just have to be very careful about your interval of integration. So this is when the actual drawing helps to organize your thoughts. And this way you're sure about what you're doing. So now if you like, we just get a 4 pi rho 5 minus y to the first power delta y. Now, when you think about this particular problem, it reminds you of the rectangular tank with just a few modifications. So now work, that is to move all of the water from the tank to ground level, So this will be 0 to 4. And now we can substitute our delta W. So this will be 4 pi rho 5 minus y to the first power dy. So this looks very similar to the last problem. We can go ahead and rig it for table ready. So again, we'll just say u equals 5 minus y and du equals negative dy. I hope these problems are becoming simpler. We keep doing the same thing over and over, and I hope your confidence is building. It's just a lot of little stuff, but the confidence you have will continue to grow. It's just that we're kind of stuck with this computation that's always like boom right here. So unfortunately, the time it may ease a little bit, it'll just come right back. So I'm not going to say that we don't have the level of computation. It will always exist in this class. So now what we can do is go ahead and adjust for the negative here. So we'll have 4 pi rho, and then we'll put in the negative 1 to adjust. And we'll have 0 to 4 5 minus y to the first power, and then the negative 1 that we need for the differential dy. So again, this is table ready. Yeah, table ready will be something Professor Ron will say quite a bit. So now we've got the negative 4 pi rho, and we can integrate in this particular case. So this will give us a 5 minus y quantity squared over 2. Even though the integrals aren't very difficult, they're certainly very important, 0 to 4. So now, if you will, we can go ahead and rearrange. So we have a negative 4 pi rho over 2. And now we can substitute. We'll have a 5 minus 4 quantity squared. And then, of course, we'll substitute the 0, 5 minus 0 squared. So when we look at this particular computation, the only difference is that we've got this extra meter that we move outside of the tank. So that's a major difference. So now, of course, the 2 will retire or absorb into the 4. So we get a negative 2 pi rho. And what do we have here? We have a 1. 5 minus 4 is 1. So this is a 1 squared. And then, of course, here we have the minus 5 squared. So this is a negative 2 pi rho 1 minus 25. And of course, this will give us a negative 24. So we have negative 2 pi rho times a negative 24. And then, of course, the negatives will absorb. And that'll give us a 48 pi times rho. Now, at this point, we can just, again, use the same technique that we used for the last problem, which is go ahead and substitute the value for the weight density, so to speak, in the MKS units. So what we can do, again, that's a nice number. So we'll go ahead and break this up. So first, we'll put the pi on the outside. So we have pi. And then if you will, we can go ahead and rewrite the 48 as 40 plus 8, just to make the computation easier. And then we have the 9,800. No decimals this time. So we have pi. So now, of course, the 0, we'll just add another 0 here. So if you will, we'll have 3 zeros. And then 4 times the 8, that'll be a 2 with a 3. And then, of course, the 36 plus the 3 will give us a 39. And then lastly, we'll just have 8 here. Again, we have 2 zeros. So 8 times the 8, that's a 4. And then the 6 here, so that'll be a 72 plus a 6, which is a 78. So now what we can see, this kind of simplifies the computation. The 400 is fixed. So we get pi. So now we've got a 400. And now we have the 8 and the 2, that's a 0. And then a 1, so that gives us a 10 plus a 7, which is a 17. And then, of course, with the 1, that gives us a 4. So this gives us 470,400 pi. And this will be in Newton meters. So again, not an overly difficult calculation, but the same kind of arithmetic that we've been doing. Again, and this is probably what your physics professors do. Just run the constants through the problem, and then of course we want an exact answer. And this is important. When you do your volumes of solids of revolution and things, you have the pi because the pi represents the transcendental number. It's not an approximation. None of the calculations, unless they say approximate, you have to give the exact answer. And so this is exact. And so, of course, if you're in the field and you need to do a nice calculus approximation, you can use your Google calculator that can run pi out to any number of decimals you like to get any kind of precision that you like. So again, just always remember that the exact computation is the preferred unless the approximation is requested. And so that means you use the symbols. I'm sure you've gotten used to going to that little pad of the Greek letters that has the pi in it. So it's going to be the same with the rho when you get to the center of mass. I've had students, it's like, well, the Professor Ron, the homework, I'm sure I did it right. And I look at their WebAssign and they've got the regular P for the rho. So go ahead and kind of put that in your memory bank so that when you see that, look at it, it is a rho. It's not the standard P, you know, like the P here. That's the P, that's the rho. Okay. Now, let's just, what we keep doing here is changing the geometry, and I've got several examples here that I want to do. Let's try, yeah, here's a good one because it uses the similar triangles. We always like our similar triangles. That's actually a theorem that's somewhat difficult to prove. I mean, unless you decide that you want to teach, most students don't get an advanced Euclidean geometry course. If I remember when I was at Texas A&M, the secondary certification students in math, they have to take advanced calculus, and of course they have to take the senior level Euclidean geometry, which they didn't like because it was extremely difficult. Very foundation, build from the foundations, and I have the book that they used. I just bought it and I worked through it, and I always would tell my honors students 3 and 4 years ago, I said, now listen, if you're not good to me, I'm going to make you prove the law of similar triangles. I said, no, we'll be good, you know, kind of thing. So let's just realize that that certain theorems that we use quite often don't always have simple beginnings, and how fortunate we are to have the law of similar triangles that's easy to use. So here we go. In this case, we have an open tank. An open tank, that means the top is open. Open tank, an open tank has the shape of a right circular cone. Has the shape of a right circular cone. And what do we have? We've got 8 feet across. 8 feet, of course, we'll have another nice picture with this one. 8 feet across and 6 feet in height. It says the tank is full of water. So now, of course, we're going to have the British units that we maybe are more accustomed to. And it says, compute the work to pump the contents over the top edge. Compute the work to pump the contents over the top edge. Kind of like all the problems we've done. We just want to take the water to the top of the tank, and then that's where we need it. And so again, we remind ourselves for the British units, the weight density is 62.4 pounds per cubic foot. So in this particular case, we want to showcase the fact that now the geometry is a little bit more complicated. So what we'll do is we'll use geometry that, or analytic geometry that describes the situation in the easiest possible way. So again, this is not buried. So maybe we're at a chemical plant or whatever. And so let's note here, we have a height of 6, so we can go ahead and mark that. And we want to just draw a nice cross section that we can, finesse to make look 3D like we always do. So the idea here is we draw our tank, the right circular cone. And of course, we have a 6 here. So we'll think of this as the y-axis. A lot of times it's great to label things, over label, if it keeps you, making good decisions. And then, of course, we can just join. So you pretty much think when you draw it where the origin's going to be. So we can think here that we have a tank situated this way. Let me do there we go, focus. Yeah, that'll get a little bit out. I mean, once I start to notice, I'm sure you all have terrific eyes. You're still 5 years old. But I'm thinking if it starts to look blurry to me, you're probably saying, oh, it's fine, but we want it to look good. So now if we look at this and we think again that we want to move all of the contents out, we're not like thinking moving the top half, we're just going to remove everything. So this implies that with this setup that we'll take y to live between 0 and 6. So again, this will respect the geometry that we've set up. Now what we want to do is just to draw in the disk, so to speak. So here we take a Y and mark off the thickness and then draw in the disk. So these problems, again, not overly difficult, but enough steps to keep you busy. So we have the delta Y here, and we have this slab of water. Now, what we can notice here is that we have this interesting lateral length here, kind of like the frustum. You know, we make the frustum from the right circular cone by chopping it off. And so this slant height, so to speak, is what's kind of giving us a little bit more difficulty. So what we can do is we can mark off this distance as, in this case, X, since the radius will vary at the very top of the tank, 8 feet across. So that means diameter is 8. We have a radius of 4. And of course, a right angle here, and then a right angle here. So now what you see is we have the distance Y, X, and then the distance 6, 4. So this is all set up for similar triangles. So now just to make that clear, I'll just take the work away from here so we can easily see it. So we have 4, we have 6, here we have Y, and here we have X. So now what you can see is that we've got our independent variable will be Y. And so we need to write X in terms of Y. That's the issue here. So let's set up the similar triangles. So by similar triangles, good old theorem from geometry, we can say X is to Y as 4 is to 6. But of course, it doesn't matter how you set it up, the result will be the same. So we have X over Y equals 2/3, 2 times 2, 2 times 3. And then of course, if and only if X is what? 2/3 times Y. So the similar triangles actually allows us to write the variable radius. For every Y, we have a different radius. And so this makes the problem a little bit more complicated than the previous ones where the radius in the last problem was fixed, because again, it was a cylinder. With the right circular cone, we have the added difficulty here. And so we easily see how we can remedy that. So now what's the last bit? We've got to move this slab of water to the top of the tank. So we can go ahead and mark that off. So this will be, I'll just note here, I'll put a little arrow here. D will actually be 6 minus Y. So here's the top of the tank, so to speak, right there. So again, very simple geometry as long as you draw a picture to organize your thoughts, just like we've been doing all along. And that, of course, is the visual aspect. So now, what about the volume of the slab? Well, just like before, we're going to have the area of the circle like we had in the cylindrical tank. So this will be pi r squared. So we have pi, and of course the radius here is X, which we have computed to be 2/3 Y. 2/3, oh, well, need to make room for the Y. Don't want to close it too soon. There we go, squared. So pi r squared, and then times delta Y. So this will give us 4/9, squaring 2/3, 4/9 pi y squared delta y. So again, the algebra is going to look a little bit different in this problem, but certainly no more difficult than what we've had in the past, maybe even easier. And so now the force will just be the weight density times the volume. So we get rho 4/9 pi y squared delta y. So if you like, just go ahead and rearrange this a little bit. We'll have 4/9 pi times rho y squared delta y. Just a lot of writing. So just make sure you don't leave out anything. That's the easiest thing to do with these problems. You know, with the disk method, you leave the pi out. You get to the end, you say, wait a minute, where's the pi? Oh, I left it back up at the top of the page. So all the same ideas moving through this problem. So now the work will simply be the force over the distance. So we get 4/9 pi rho y squared. I'll go ahead and squeeze in the distance, 6 minus y delta y. So again, we have force over the distance. We take the product here. And so now if you want, you can go ahead and multiply this out. That's going to help us when we write our integral. So we have 4/9 pi rho, and this will give us a 6y squared minus a y cubed delta y. So now we've got our interval of integration. We're basically set up with the integrand, at least what we know for each subinterval, and then we let the norm of the partition go to 0. So this implies, again, the work to move all the contents of the tank to the top edge. So we have work equals, again, 0 to 6. And here's our delta W. So we have 4/9 pi rho, and we have 6y squared minus y cubed dy. Okay? So again, this is just add 1, divide by the new power, so to speak. Now, one important thing is, like I say, don't underestimate the law of similar triangles, and be careful when you run the ideas through about just the basic geometry. That's where it's easy to slip up and just make a very simple error. So now let's go ahead and clean this up. Let's factor. So we have 4/9 pi rho integral 0 to 6. 6, let me make sure that looks like a 6. Oh, that's kind of bad, sorry. 6y squared minus y cubed dy. So now we're going to add 1, divide by the new power. So we have 4/9 pi rho. So we have 6 times y cubed over 3 minus y to the 4th over 4, evaluated from 6 to 0. So, or 0 to 6. And what's nice about this problem is that, again, the number theory helps us to get to the finish line in a fairly simple way. Now, let's just kind of look at this. This gives us 4/9 pi rho. And then as we're looking here, we automatically can retire the 3, because that absorbs into the 6 to give us a 2. And then, of course, we get the substitution here. Of course, the lower limits give us the 0, which we're very happy to get. And then, of course, upstairs, we get the 6 3 times. And now we get the 6 4 times. And then, of course, in the last bit, we just get 0. So I'll just put 0 there, just kind of like we all know that goes away. So again, that gets annihilated. So now we can clean this up. So we have 4/9 pi rho. And now we can see we can retire, in this case, the 4. So we're going to rewrite this as a 6 squared, since we're going to have to use 2 6s to retire that 4 there. So we've got 2 times the 6 times 6 squared. Yeah, that looks good. And then we have, let's just say 2 times 3, 2 times 3, and then a 6 squared. So we can just use the basic number theory to get rid of the fractions. So we're not going to have, 13 downstairs. So we have 4/9 pi rho. And now we've got the 12 times the 6 squared. And then, of course, here, notice the 4 is the 2 times 2. So that retires this 2 and this 2. And of course, this is retired, leaving us with a 3 times a 3 times a 6 squared. So this gives us 9 times 6 squared. So again, we retire the 4. So we get 4/9 pi rho. And now you can see the way I factored this, we get rid of the 6 squared. So we have times 6 squared. And that leaves behind the 12 and the 9. So all the fractions are going south, and we have no problem with that. So now notice we've got 4/9 pi rho. And then, of course, the 6 squared is just 9 times 4. And then, of course, 12 minus 9 is a 3. So now we can see the 9's absorb. So what are we left with? 12 pi rho. Now, the interesting thing, and let me just check to make sure I've got all of my numbers here. I've got the 9, I've got the 4, and then we're going to have the, I think I dropped, did I drop anything? Let me just make sure I didn't drop anything. So we've got the 9. That looks good. We got the 6 squared. Oh, I've got another copy of let's see, I've got the 6, I've got the 4. So that's a 16. Let me just make sure I've got everything here. Looks like I dropped something somewhere. So I've got this, I've got the 6 squared, 4/9 pi rho. And then we've got the 3 and the 3, which we get rid of there. And let's see here. So let me just make sure I've got all of the stuff here. 6 squared, which I kind of, let's see here, 3. So we've got the 3 here, and we've got the 4. Yes, the 4. I knew I dropped that 4. Notice here, this is 9 times 4. And I've got the 4 here, but I just ignored it. And so that's going to be a 4 times 12. So I did it correctly. I just ignored this. When it comes to perfection, I think that's what I was blessed with. But the 4 is right there, and I somehow thought I had lost it. So that's a 4 times a 12. So I have my 48. Good for me. I didn't lose it. It just looked like I had lost it because I disregarded it. So now let's see what we get. So we've got 62.4. And what I did in this particular calculation, let's go ahead and break this up and retire some of the decimal. So this will be pi, and we've got 40 plus 8, and then we have 62.4 from here. Now let me get one more sheet of paper to move the calculation down so I can finish it. So now, so at this point we get pi. Now notice we can retire the decimal here with the 0. So that's going to be 4. That's our friend, 624. And then of course the 8, we're stuck with the decimal. So we're going to get a 32. So we get a 2 and then a 3. That'll be a 19 with a 1. So 48 plus 1. So that's 4992. And then of course one decimal right there. And now we can multiply this. That'll give us our 16 with a 1. That'll be a 9 and then a 2, 4. So we've seen that calculation before. Plus 4, 9, 9. Very close to 500, wouldn't you say? 0.8. So this gives us pi. And now we can just add these. We've got the 0.2. So we have the 6 plus the 9, that's the 5. With a 1, that's going to be a 10 plus a 9, which is 19. And then a 1, that'll give us a 5 plus a 4, which is a 9, and a 2. So this will give us 2995.2 times pi. And in this case, we have foot-pounds. Now, again, when you're doing these calculations, and this is what I'm talking about, it's always good to be able to go back, you know, and say, okay, I did this and I did that. Oh, there's the factor, it's right there. If you write out the calculations like we're doing, you can always go back and check your work. And so when I look at your work for the test, I want to see the computation. Of course, it won't be this. I mean, it'll be the other types of problems, but it'll be very similar to this. So what we're seeing, at least as a maturity step from Cal 1 to Cal 2, is that in Calculus 1, you do lots of work in arithmetic, but the problems aren't as long-winded. They start to get really long as you get to optimization and then the Riemann sums and things of that nature. But we're seeing here the level of maturity rises as the problems are just longer. And that really is what makes the work a little bit more difficult. Even though you're doing the same thing, you're just doing more work. So now what we can see is that just for this particular tank with the more difficult geometry, we get work to empty the tank, basically, what is that, 3,000 times pi, so over 9,000 foot-pounds. So when it comes to moving liquids around, that you got to have plenty of energy source. So those of you that become a hydrologist or you work with the city, you know, in moving water around, you'll be a very busy person. The dams, the Niagara Falls and the Hoover Dam, again, just marvels of nature and marvels of engineering. I mean, it's amazing. That's one thing that's a little bit frightening when you think about that huge wall of water that's being held back and all of the physics and all of the calculus that we see at motion there. It is truly amazing. I mean, the appreciation for math should be there, even if you don't really like math. You all like math, but not everybody likes it. But the appreciation should be there. Now, there's a interesting example here that, let's see, that I want to set up. It and then I'll share another one with you, and I'll probably add another one of these on Wednesday in the review, just as an additional problem. I want to talk about an example that deals with a chain, uh, just to kind of give you an idea of how you work with that. So we moving liquids around. There's also a problem in your WebAssign where you have a hemispherical tank and you're basically filling the tank from the bottom, of the tank. So you can set up the hemisphere, so it rests on the plane and do your y-axis like we've been doing. So again, the geometry will be fairly straightforward, but always remember, what does the slab of water look like or liquid look like? That geometry is really important because it guides you through the delta V. So here, for this example, I thought this one was interesting. We have a 50-foot chain. So a 50-foot chain weighs, so this has a linear density, 4 pounds per foot, okay? 4 pounds per foot, and it hangs from, this is for instance, when you think of a retracting device, from a winch 50 feet above the ground, above ground level. And then it says, just to make it interesting, this is what I was talking about at the beginning of class, a 500-pound load is attached. And then the question is this, or the directive is this. It says, compute the work to retract the entire chain. So just remember on the test, there'll be a sufficient number of problems to keep it fair. So when you look at the practice test, you'll see about what I expect of you. You'll have plenty of time. I'm always gracious with the time. That's one thing about the online. You get the padding of having extra time, and I don't ever want you to think that you don't have enough time to complete the test. I want you to have some level of comfort. I'm not a taskmaster, even though some students call me that. That could be farther from the truth. I just want you to learn and I want you to work hard. And when you do that, wow, you can do amazing things. Now, when we think about this particular problem, we've kind of got two ideas going on. Let's think about the fact that we have this winch that's 50 feet above the ground, and we've got this. So you're thinking, okay, well, we'll just do this. We'll just keep it simple. So we can think of this as 0 and this is 50 if we put our axis right here. So we're thinking, okay, here's the chain. Now I'm not going to be Rembrandt with this. I don't think I do too well with the chains. So we're going to say that y lives between 0 and 50. And so we're going to have the chain, which again is a calculus problem because it has a linear density. And as you retract it, again, you've got less chain to move. And then you've got the load, which is kind of the simple part of it. When you don't have a variable force, the load weighs 500 pounds. It doesn't vary. The chain, however, does vary in the force that it exerts. So you've got an easy part and a simple part. So now we can think, all right, so we take some y here and we take a little piece of this, and that's just delta y. So here's our y, excuse me. And we think, well, we've got to go a distance, 50 minus y. So when you look at this, you're thinking, well, there's nothing to do. It's so simple. So we have like a change in length, which is delta y. And then the force will be 4 pounds per foot times the delta y. And then it's like, this is so simple compared to what we were doing, but it's important. And so we move this a distance 50 minus y. So in this case, we have 4 times 50 minus y delta y. So what we get from this is variable, and let me write this down. I thought this was good. This just kind of a refreshing problem. Variable, in this case, variable force. In this case, constant force. And so now we're thinking, okay, well, what do we have here? The work done here is 50 feet times 500. That load that's attached has a constant force and it moves 50 feet. So this gives you got what? 3 zeros, 25, 1, 2, 3. And that'll be foot-pounds. So that's kind of like the freebie part of the problem. You're kind of stuck with that. And then the calculus part is retracting the chain that has a linear density. So now this part is done. And so whatever we get here to find the work will require adding the two. And I want you to do these separately so you get the logic. So now for the chain, this says that our work, I'll just say work sub chain. And I'll just say this is just work sub load, so to speak, maybe to differentiate them. So we have 0 to 50. And then we have our delta W. So we have 4 times 50 minus y delta y. So that looks kind of familiar, right? So U, our friend, 50 minus y du equals negative dy. So we can rig that to make it table ready. So we'll factor the 4. So we have 4 and a negative 1. 0 to 50. And then we have 50 minus y to the first power, negative 1 dy. Well, the beauty of calculus is that it affords us some really nice techniques. Unfortunately, when we can't do a nice technique like this, everything gets spread out with horrible powers and we're just stuck with the arithmetic. I'll share a problem that I've answered to one of your classmates with the shell method. And of course, it would have been much easier to do with the disk method, but the problem said, okay, I want you to practice the shell method. And of course, the arithmetic is just there, like I do. You factor things and you work it out. But sometimes the algebra doesn't support your work as much. You just have to do the computation and just finish it. And when it's done, it's done. So we'll see that a lot more. So now let's do the add 1 divided by the new power. This is table ready. So we have a negative 4 and we have 50 minus y squared over 2 evaluated from 0 to 50. So now, of course, we can bring the 2 out. So we have negative 4 over 2. And then we can substitute the 50. So that will annihilate. And then, of course, we get 50 minus 0. All right. So now what do we have? We got a negative 2. And now we have a 0. And now we've got a 25 with 2 zeros. So we have a 2500. Now, of course, this will give us a negative 2 times a negative 2500. The negatives absorb. and we get a 5,000. So at least we weren't having to tackle a lot of um, extra arithmetic like we've had on the previous problems. And so now for the chain, this gives us foot pounds, 5,000 foot pounds. And so therefore, the work, now we can just call this plain old work because the problem says compute the work to retract the entire chain. So when you think about moving chains and things, I mean, this is a common occurrence. I mean, engineers deal with forces, especially mechanical engineers, civil engineers. I mean, it's like, okay, boom. And it's a constant. I mean, you think about designing something and then you go to sleep at night and think, oh my gosh, did I do this? Did I do that? It's like the stress is high. You know, you think about what you do. It's kind of like, you know, Professor Ron writes a test and then at 3 o'clock in the morning, oh, wait a minute, I need to put this in the problem. You know, it's varying degrees. It's kind of like as a math professor, you're always thinking about things. As an engineer, as another STEM professional, as an engineer, you'll be thinking about things constantly. But the thing is, you always want to be thinking, even when you're executing. But you don't want the thinking to override what you're doing. You know, my mind is always racing when I do math, just like when I do music. But you wanted to support what you're doing because you've done your due diligence. And so just remember as you think about these problems, step by step, just as I've tried to teach you to say, okay, here's what we need to do, break it down, and then work forward. So now the total work, again, will be the chain work and the load work. So we say work of the chain plus work of the load. And that will give us, well, the chain work, 5,000. And then, of course, the load work, 25,000. And that gives us 30,000 foot pounds. So the idea here is really, really important that even if we aren't tested on this material, the same type of executions will be done in the problems you've already done. That's why I kind of like having this during the testing week, because it basically emphasizes the type of calculation that we've been doing. Now, what I said about Wednesday is that I'll do some problems that kind of encapsulate everything. I don't always do this, and I'm thinking maybe this time it'll be more refreshing. And like I say, you can take from it. It's like, well, I understand how to do this, Professor Ron, or whatever. But I just want to kind of give you an overall review. Would be like the types of problems that you would see on the test, which are actually the types of problems I've been doing. And just remember that the types of problems will mirror what we've been doing. You know, I don't look at a test as being, oh, look at me, surprise. No, it's not that at all. If I've talked about something in lecture and made a point of it, then you can be assured that you're going to see it on the test. That's how I work. I don't, you know, there might be a problem that requires you to think a little bit more. You know, you've got to do a little bit more algebra, but it will be things that will be reasonable. Okay. I relish the fact that you've had pre-calculus, college algebra, and calculus 1. So there are certain things that I can assume you know how to do, but I'm not going to throw out something that's something really obscure, some trig identity that we haven't used. I mean, I'll keep everything nice and reasonable. But just remember, the best way, and students ask me this all the time, what's the best way to prepare? Just make sure you've done your homework, work back through everything, work through the practice test, work through the lecture notes, the PowerPoints. Just do as many problems as you can do. And then when you set to do the test, then you can write out your work, knock it out, scan it, and you're done. So that's really what I want for all of you all. So I'll have two sessions today. I've got one early and then I've got one late. If that will work for you. Again, continue to send your questions with the WebAssign. I always appreciate the WebAssign questions because they give me ideas about things that may cause you difficulty. Just remember, every time you use an idea from the class, make sure you're using it correctly. On occasion, there'll just be a little bit of a slip, but you know what? When you make the mistake, it really does cement the idea in your head. So I appreciate your attendance today, and I look forward to doing some review work on Wednesday. So enjoy this beautiful weather. You know, only in Houston, right? So if I see you at the office hours, that'll be good. If not, I'll see you online with WebAssign, and then we'll meet back again on Wednesday. So everybody have a great day.